Welcome to this lecture on digital fabrication techniques. There's a large collection of manufacturing principles available. We will discuss the main ones that might enable you to design new products or services. The main digital fabrication technologies are additive and subtractive. Furthermore, there are some other techniques that might be applicable for specific uses. So let's discuss the first, additive fabrication, also known as 3D printing or additive manufacturing. Additive technologies have been grouped in the following 7 categories: fat photopolymerization, material jetting, binder jetting, material extrusion, powder bed fusion, sheet lamination, and finally directed energy deposition. This is a vast collection of methods that came into existence in the past 3 decades. And we will probably see new categories in the years to come. So let's have a quick look at the present state of art. This overview is of great reference. It shows the main additive technologies on the top. Each might exist in several variations, depicted in the 3 bubbles below them. Subsequently, each of them apply for specific materials, as shown below the bubbles. The cup stands for plastics, while the C-shaped magnets identifies metals. We will now discuss technologies in each of the categories. The oldest additive manufacturing technology is vat polymerization. It starts with a vat of photopolymer. This is a liquid that changes into solid when exposed to ultraviolet light. This light can be projected using a laser, projector or an LED display. And each layer of the 3D model is cured individually to form the complete model. One of the advantages of this technology is the ability to build models with fine details. However, overhanging structures required so-called support structures. And recent developments have shown that the building speed can be dramatically increased through clever use of the chemical reaction that causes the solidification of the photopolymer. Material jetting is a process that applies inkjet technology. You might know inkjet from your desktop color printer at home. Instead of jetting ink, the liquid is used that becomes solid. Small droplets of material are selectively deposited through by one or more inkjet heads. The heads move over the platform and build up an object layer by layer. And the material used is usually a photopolymer, which is cured directly with a UV light. At the same time, a secondary inkjet, the head, deposits support material, which will be removed after printing. Material jetting allows 3D prints with various properties, like toughness, transparency, or a rubber-like flexibility. And by using multiple heads, it enables combinations of different material properties and colors. The binder jetting technology uses thin layers of powdered material to build up an object. A binding agent is sprayed from a printing head to bind the powder together. When the first layer is cured, the bed moves down for the next layer, and the material used is typically plaster, which results in low-cost but relatively brittle prints. By using a regular inkjet print head, binder jetting also allows colors. In material extrusion, a heated nozzle melts and extrudes a material. The nozzle moves over the build platform to build a layer with the extruded material. And once a layer is ready, the nozzle continues the next layer on top of the previous one. Some models require a support structure to be printed for overhanging structures. And because the process is relatively simple, it has become a popular choice for home-built systems and low-end additive manufacturing machines. Specifically, the open source project RepRap stated that is based on this technology. And in turn, the RepRap has sparked the development of many commercial desktop 3D printers, which have now become widespread today. Just as binder jetting, powder bed fusion is based on powders, but now with plastics and metals. a layer of powder is selectively heated and fused, usually by a laser. And after one layer, a new layer of powder is deposited on top of the previous layer, and the process is repeated. Powder bed fusion results in products that perform almost as good as traditional manufacturing methods, such as casting or machining. It already has found its use in medical, aerospace, and in automotive industries. Sheet lamination, also known as layered object manufacturing, refers to the basic method of layering plastic or paper and cutting each layer by the correct contours and bonding it to the previous layer by glue or a similar agent. In the case of using paper, inkjet printing can be used to add color to the sides of each layers, thus resulting in a full color result. However, the result is a solid, almost wood-like prototype. Furthermore, this technique requires manual post-processing, as excess material needs to be peeled away. As a low-cost solution, it can be useful for prototyping urban models or similar 2.5-dimensional models. The final additive technology is direct energy deposition. Here, both material and solidifying principle are cast at the workpiece at the same time. Often, the deposition and fusion is done using an articulated robotic arm. And this has two advantages. You can print in different grow directions, or you can print on top of existing products. And in practice, this method is used for high-grade materials, such as stainless steel and titanium. And you might know of similar technique where welding robots are being used to print large workpieces. Apart from the expensive setup, the print quality is currently very difficult to control, and as such you will find these only in research labs. As discussed, a variety of materials can be used in additive manufacturing, ranging from well-known plastics such as PLA, ABS, polyamide or nylon, and epoxy-like resins. Metals can be used either directly or through mixing with plastics. And finally, other materials such as ceramics and wax open up applications in, for example, aerospace and jewelry industries. More exotic ones, such as biocomposites for printing organs or food, can use similar techniques, but these are restricted in use due to certification. Common challenges of additive manufacturing techniques are first of all anisotropy. By the layered manufacturing, the strength of the objects is different in different directions, and often the horizontal plane is better than the vertical direction. Furthermore, this often also influences the visual and tangible properties of the printed objects. Careful planning of the printing direction, also known as the build-up orientation, is required. A second problem arises from residual stress during the solidification process. This might lead to deformation while subsequent layers are deposited among each other. This is often solved by adapting the build-up orientation and, if necessary, adding additional support structures to minimize warpage. Finally, although 3D printing represents an exciting manufacturing solution, we know little about its environmental impact. Specifically, the recycling and energy consumption during manufacturing and the logistical processes should get more attention. The second set of digital fabrication techniques is subtractive. Here we start with stock material that is removed by a digitally controlled system. For today we will look at two well-known and powerful approaches. Laser cutting can cut through and engrave several sheets, for example plastic, wood and leather. This technique is extremely fast compared to additive manufacturing, while modeling can be done in basic vector drawing packages, such as CorelDRAW or even PowerPoint. More elaborate, either 2D or 3D digital fabrication can be performed with CNC milling, a technology that caters for a large variety of materials. These machines can run up to 7 degrees of freedom, allowing making intricate workpieces. For decades, this already has been used in manufacturing and tooling. However, it requires more pre-processing and often needs to be operated by well-known staff. Apart from additive and subtractive technologies, there's a growing set of methods that are also digitally controlled, but they work in different ways. We will discuss two of these. First, there's material deformation, specifically digital sheet metal forming, that uses heat and force to deform a planar sheet point by point. Some body parts in the automotive and train industry use this method to make special parts without having to invest in molds for stamping. Other fabrication technologies are being used in fabric and textile manufacturing. Here, specifically, digital knitting is of interest, because it can create intricate shapes without waste materials. For example, this Japanese knitting machine on the left can make a complete sweater to your own shape in less than 1 hour. Because you're not limited to wool or cotton, you can fabricate smart fabrics with conductive yarns. And in the past years, simplified versions of these have been developed by open source projects, allowing you to create your own garment manufacturing system. Here, for example, a desktop version of such a knitting system which was just released. At the size of a refrigerator, it still is too large for everyday homes. But you will never know what will be next. It may be a new chemical reaction or the use of DNA. Help us in challenging the future of digital manufacturing.